So as of yesterday, we have more or less concluded the material that we are going to talk about concerning first-order differential equations. First-order differential equation contained at the most a first derivative, no second derivatives, no third derivatives, etc. And we have concluded all the different varieties of first-order differential equations that we're going to solve. We saw how to solve them in the case that they were separable. We saw how to solve them in the case that they were linear. We saw how to solve them in the case that they were exact. We saw how to solve them in the case that they could be converted to a differential equation that was separable or linear. We saw how to represent them graphically, for example, using a slope field, or for an autonomous ODE, using a phase chart. And then we saw how to get a numerical estimation to a solution for a first-order ODE, using either Euler's method for speed and efficiency or RK4 for accuracy. To finish talking about first-order differential equations, we're going to spend the next couple of days looking at some specific applications of first-order ODEs in real-world type problems. And today we're going to talk about exponential growth and decay. I've already done a few problems of this nature, sort of sprinkled throughout our previous videos, but let's focus today on exponential growth and decay. And let's do a couple of example problems. For example, let's consider simple exponential population growth. The population of bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. So I'm going to call P of t the number of bacteria present at time t. And if I translated what they just said to me into a mathematical sentence, I would say that the rate of change of population, what we would call the derivative of population, P prime, is proportional to, so it's equal to a constant times the population. Now, it says after 3 hours, when the t is 3, it is observed that 400 bacteria are present. So I'm going to make a note that P of 3 is equal to 400. That's the population at t equals 3 hours. If I check at 10 hours, 2,000 bacteria are present. So then let's try and figure out how many bacteria there were at time 0. How many bacteria there were initially. Now, in solving this problem, we don't yet know this precise value of r. So let's try and solve this equation just leaving r as an unknown constant. And after we do that, let's see if we can figure out the value of r, maybe using one or maybe both of these points that were given to us. P of 3 equals 400 and P of 10 equals 2,000. So this equation is separable. Bring P over, integrate both sides, solve for P, and we get a population that is given by the exponential function k e to the r times t. So we've actually wound up with two unknowns in our solution. One is the unknown growth rate, called r, and one is the unknown constant that came from solving this ODE, the constant called k. So let's see if we can figure out these values using the 2 points that are given. So let's see what happens if I plug in t equals 3. 400 is the result, and that's equal to k times e to the 3 times r. Meanwhile, 2,000 is equal to k e to the 10 times r. What I'm going to do now is I'm going to consider what would happen if I divided these two expressions. On the left-hand side, I'll have 400 divided by 2000. And on the right hand side, I'll have k e to the 3r, k e to the 10r. The reason why I'm interested in dividing these expressions is because if I divide them, then I'm able to cancel out k, and that leaves me with an equation that only has one unknown. Because the equation only has one unknown, I can then solve for the value of that unknown. 1/5 is equal to e to the -7 times r. So -7 times r must be equal to the natural log of 1/5. So r must be equal to -1/7 natural log of 1/5. Now that I've found the value of r, I can plug that number into either one of these two given equations to eliminate the unknown r from those equations and leave the single unknown k. Now you can use either one you want. I might just decide to use the left one arbitrarily. 400 is equal to k e to the -3 times 1/7 natural log of 1/5, -3 because of 3 times r. So if I go ahead and I simplify this quantity on the right side, then I get 400 is equal to k times 1/5 to the power -3/7, which implies that k is equal to 400 times 1/5 to the power +3/7 if I move that quantity over to the other side. So what does our differential equation become? If I write it in exact terms with no decimal approximations, we now know that the population at time t is equal to 400 1/5 to the power 3/7 e to the power -1/7 natural log of 1/5, because that's our r, multiplied by t. And all I've done is I've just gone back into the general equation that we found, p equals k e to the rt, replaced k with the value that we calculated, and replaced r with the value that we calculated. So now it's time to actually answer the given question. And the given question was, how many bacteria were present in this population initially? The keyword initial means that no time has passed. So I'm going to plug in 0 for time, no time, which is going to cause the entire exponential term to become just 1. And all that will be left is the value of k. Now to make this more meaningful, I'm going to go ahead and get a decimal approximation for this. And this is approximately equal to 201 bacteria. So that's how I would solve this particular problem. I would go ahead, set up an ODE by translating the English statement that they had given me into a mathematical statement, solve that ODE, fill in the blanks of the unknown constants given the 2 points, and then use that solved equation to answer the given problem. Let's do something similar with the second example, which is concerned not with population growth, not with exponential growth, but which is concerned with radioactive decay, exponential decay. So initially we have 100 milligrams of some radioactive substance. So if I might call A of t the amount at time t. So what they just said to me was that A of 0, the initial amount, was equal to 100 milligrams. Initially 100. Now after 6 hours, so when the time is equal to 6, the mass, the amount, has decreased by 3%. So if I take 3% off of 100, now I'm down to 97. So assume that the rate of decay is proportional to the amount of the substance present at time t. So the rate of decay, the rate at which the amount is changing due to decay, which I'll simply call A prime for simplicity, is proportional to, is equal to some rate times the amount that is present, which is what we're calling A. Now, as before, we can go ahead and solve this differential equation using the standard trick. It's of exactly the same form that we had for the population growth, so we get an answer of exactly the same format. The amount at time t is equal to a constant called k multiplied by e to the RT. So let's go ahead and then try and use these two pieces of data to find the two constants in the equation. The one that seems the nicest to start with, in my opinion, is the one where t is equal to 0. Because if we plug in t equals 0, then something very similar to the previous example happens. The e to the RT will just become 1, because e to the 0 is equal to 1. And so we can immediately get our value of k. K is equal to the initial value, 100. So now that we've determined the value of k, let's go ahead and determine the value of r by plugging in the second point, which says that we're going to have 97 milligrams of this substance after 3 hours have passed. So I'm going to replace the TE with, 6 hours, 6 this time, and we now know that the K is 100. So 0.97 is equal to e to the 6r, which means that 6r is equal to the natural log of 0.97. And therefore r is certainly equal to natural log of 0.97 divided by 6. So now we have finished filling in the blanks of our equation. The amount of the substance left after t hours is given by the initial amount, 100, times e to the natural log of 0.97 divided by 6. That's our r value, and r was multiplied by t in the exponent level. Now this is a good time to remind ourselves what the question was actually asking for, and it says find the amount remaining after 24 hours. So in other words, find the amount when t is equal to 24. So all I have to do is plug 24 into the equation where t lives, and let me go get a decimal approximation using a calculator. Okay, so I've gone ahead and calculated that number off to the side, and that number is equal to 88.5 milligrams rounded to 1 decimal place. Follow-up question, what is the half-life of this substance? Now the half-life of a substance is the amount of time that it takes for a quantity to decay to half of what it originally was. So our substance initially had 100 milligrams, and we are now interested in what time would correspond to having half that, to having 50 milligrams. But now that we've got our ODE completely solved and filled out, all that we need to do is go grab it, stick 50 in for the output, and then solve for t. So, isolating the exponential, then applying natural log to both sides, find that the time is given by the natural log of 50% divided by the natural log of 97% multiplied by 6. As always, let's go ahead and get a decimal approximation for this value. And we find that the half-life of this substance, the amount of time it would take for the substance to decay to half of what it originally was, would be 136.5 hours. Now, we have done this for this mysterious substance, set up a differential equation, solved it, but of course this could be applied to any substance which decays exponentially. For example, any kind of actual radioactive decay problem, including carbon dating, as well as the metabolization of substances in the body. For example, if I recall correctly, the half-life of caffeine in the human system is roughly speaking 6 hours. So if you ingest caffeine, you can use a problem set up like this one to sort of track how much caffeine is in your system after certain periods of time. Let's consider the case of carbon dating via tracking the amount by which carbon-14 has decayed in a dead organism. So the half-life of carbon-14 is 5,730 years. So what we're saying is that whatever amount we had initially, let's just call it A0 for short, if I plug in t equals 5730, then I'm definitely going to have half of whatever amount I started with, half-life. It says the decay rate of carbon-14, so rate of change, A prime, is proportional to, is a number multiplied by the amount remaining. So let's find the percent of C14 left in an object which is 600 years old. So I'm just going to cut to the chase. We've solved this equation on the left-hand side like 4 times now. This would have the format k e to the rt. And by now we also have seen several times that for an exponential function like this one, the value of k corresponds to the initial amount. Now the initial amount hasn't actually been given to me, so I'm just going to use a sub 0 as a more meaningful placeholder. The amount at time t is equal to the initial amount, e to the rt. Now, at minimum, in order to stand a chance of being able to actually answer the question in this problem, I'm going to have to use the given data point that if I plug in t equals 5730, then I'm left with half of whatever I started with. So let's go ahead and let's plug in that information. If I set t equal to 5730, then the output is going to be half of the initial amount, A0. Now the important thing about this problem is that because A0 is present on both sides, it can be eliminated from both sides. And this leaves me with an equation containing only one unknown. And that's an equation that we can solve. So if I apply natural log to both sides, natural log half is equal to 5730 times r. Then the rate, the decay rate for carbon-14 could be expressed as natural log of 1/2 divided by 5730. So the amount after t years is equal to the initial amount multiplied by e natural log of 1/2 5730 times the number of years that have passed. Now at this point we've used all the data points that we have. So let's go ahead and plug in t equals 600 and see if we can answer the question posed. Find the percent of carbon-14 left in an object that is 600 years old. Now I went ahead and calculated that value off screen. What happens to this E factor when t is 600? and it looks to be approximately 0.93, which is the same thing as 93%. 93% of corresponding to multiplication, 93% of the initial amount. So even though we have never actually learned the initial amount, we do have enough information to answer the question that was posed. What percent of the initial amount is remaining after 600 years? 93% is remaining. Another quantity that can be represented by using an exponential growth or decay model is continuously compounding interest. This would represent, for example, the rate of growth of something like land or art or some other physical asset which is growing in value over time, but is not growing in value as a result of something coming in and like depositing actual interest into an account. So, when we compound interest continually, the amount of money that the object is worth increases at a rate which is proportional to the amount present at time t. So as usual, we get our exponential differential equation that says the derivative of the amount is equal to some number times the amount, proportional. Now in particular, we're told here that R represents the annual interest rate. Find the amount of money accrued at the end of 5 years. So find the amount at the end of 5 years. When $5,000 is initially deposited, so that's our initial amount, $5,000, in a savings account drawing 5% annual interest compounded continuously. So our rate is 5%, or converted to a decimal, 0.05. So in this case, we can actually fill in the value of R before we even go and try and solve this equation. S prime is equal to 0.05 times S, and therefore 1 over S prime is equal to 0.05. So the natural log of the absolute value of S is equal to 0.05 times T plus C, and therefore S itself is equal to K e to the 0.05 times T. So now let's use this initial condition to fill in the value of K. And as usual, when you have exponential growth, the initial value is an exact match to the K. Let's quickly verify that by plugging in 5,000 for the S value, plugging in 0 for the T value, and sure enough, K turns out to be 5,000 exactly. So the amount that the investment is worth after T years is equal to the initial amount, E, to the interest rate times the time. So now let's go ahead and answer the question. It says, what is the value of S when T is equal to 5? Now that we've solved the differential equation, all we have to do is plug in T equals 5. And the investment is now worth $6,420.13. Now, realistically, you're not going to find a quote-unquote savings account with an interest rate that is this high. 5% interest on a savings account is a fantasy. But this interest is actually pretty reasonable for something like a mutual fund, an index fund if you're investing in the stock market. Final example of differential equations as applied to problems involving exponential growth and decay. Let's go back to Newton's law of heating and cooling. So recall in video, let me look it up real quick. Okay, so from video number 8 apparently, when we were practicing using integrating factors, we saw that if you took the general solution to the ODE corresponding to Newton's law of heating and cooling, then the solution was given by the temperature at time t is equal to the temperature of the environment plus the difference between the initial temperature and the temperature of the environment multiplied by e to the kt. We worked hard to get that result, so I am going to recycle and use it again here. So now let's figure out what the constants T0, T environment, and K might be for our particular problem. So a dead body was found in a closed room of a house where the temperature was a constant 70 degrees Fahrenheit. I'm sorry if this is a little morbid, folks, but I always like to do things that are a little bit outside of the box from time to time. So the temperature in the room, the temperature of the environment for this particular problem is 70 in the units of degrees Fahrenheit. Now at the time when the body was discovered, the body's temperature was 85. So I'm just going to say the temperature at the time of discovery was 85. 1 hour later, so the temperature at the time of discovery plus 1 additional hour. Now the body's temperature is 80 degrees. So it says, assuming that the time of death corresponds to time t equals 0, and that the core temperature at time t equals 0, what we're calling T naught, was 98.6 degrees, determine how many hours elapsed before the body was found. So what we're basically trying to do is figure out the time of discovery. If the time of death is equal to t equals 0, then the time of discovery will tell us how many hours have passed since the time of death. Now for convenience sake, I'm going to go ahead and nickname the time of discovery by maybe t sub d. That seems natural, doesn't it? So with that notation, let's go ahead and fill in as many blanks from this general solution as we possibly can. So the temperature of the environment was 70 in the units of degrees Fahrenheit. And if I take the difference between the body's initial temperature and the temperature of the environment, then I get 28.6 e to the kt. So now let's figure out what is going on with the k value. That's really the only unknown left in this problem. For that, let's try using our final two data points. The temperature at the time of discovery is equal to 85. And the temperature 1 hour after that is equal to 80. So let's go ahead and simplify both of these expressions. For example, by getting 70 out of the way, 15 is equal to 28.6 e to the k times td. 10 is equal to 28.6 e to the k times the time of discovery plus 1 additional hour. Now, in our very first problem, I remember that when we got into a situation like this one, where we had two exponential equations containing two unknowns, the technique that we used was to divide the two equations. So let's try that now, and let's see if it turns up anything useful. I keep forgetting to make it full screen. So if I take 15 divided by 10, that will be equal to the 28.6 e to the k times the time of discovery divided by 28.6 e to the k times the t of discovery plus 1. So let me just go ahead and distribute that k through. Now I've succeeded a little bit because I've managed to eliminate this 28.6 by doing this division. But we can simplify this even further if we use some exponent properties. If I go ahead and take this exponential in the denominator and split it up into a product, e to the k times d multiplied by e to the k separately. Now I can eliminate the e to the k times t sub d, and I am left with an equation once again containing only one unknown. So 1.5 is equal to 1 divided by e to the k, and if I reciprocate both sides, e to the k is equal to 2/3, which means that the k value must be equal to the natural log of 2/3. Haha! So now one of the unknowns in my equation has been filled in. If I scroll back up, in particular, if I use that value of k in this equation, then I will be left with an equation that has only one unknown, the unknown t sub d, which is the quantity that I'm looking for. So if I go ahead and plug that value of k into that equation, I'm now left with something that can be solved for t sub d. Get 28.6 out of the way. Take the natural log of both sides. And then divide. The time of discovery would then be equal to natural log of 15 divided by 28.6 divided by the natural log of 2/3. And so the time of discovery was about 1.6 hours after the time of death. You can use that to help compare against the alibis of any suspects in the case, that kind of thing. So that concludes today's material. Nothing new, really. We just practiced applying some principles that we already knew in a couple of real-world application problems. Probably the most important thing to do in these problems is to just read the question carefully and to take all of that English giant paragraph and try and translate it into mathematics. Translate it into a differential equation, and then translate any data points that you're given into something a little bit more concise that you can plug into the solution to your differential equation.